Get your curiosity right.
Mad Bricks webcast,
Where the human spirit flies. Mad Bricks webcast. Where the human spirit flies.
Hey, welcome to the Medbix webcast. This is Ramana Raju. I'm the host. I'm in Livermore, California. Livermore is the epicenter of innovation in physics. Where they found a nuclear, where the cyclotron was born here, and the nuclear physics is really invented here. Nuclear physics here, it is the epicenter of the physics world of physics. National laboratories are here, Livermore National Laboratories. There is an observatory is also here. It's a very state-of-the-art, the most of the nuclear military kind of things also here, but it is the most advanced scientific place. I am always, when I was a physics student, that is my passion to go to Livermore. Now I'm stuck in Livermore today because of some business thing. But let me bring my co-host. She's joining from Port Myers. She's a beautiful, blonde, bold, brainy, all of them, combo. So let me bring Susan to the table. Susan.
Good
Welcome,
evening,
Susan.
Ramana. Good evening. I'm so excited you are stuck in. Did you say Livermore? Is that what it's called, Livermore?
What is that?
Is that the name of the city? What's the name of the city?
Livermore.
Livermore. What a fascinating. I mean, how many areas of physics can there possibly be? Now, this is nuclear physics. It's fascinating.
Yeah,
Very
there's
exciting.
the epicenter of nuclear physics. It was born in epicenter here.
Phenomenal.
The cyclotron, where you produce isotopes now, cyclotron was invented in the Livermore here.
You have to tell us what that is. Not everybody knows what a cyclotron is.
A cyclotron is where you do contrast agents. For example, you do any contrast agent you want to produce, FDG or a technetium. All these isotopes are produced. They are produced in the cyclotron. Cyclotron is an accelerator, particle accelerator. It moves fast and fast and fast and fast, moves there and produces the isotopes.
That's very exciting.
Besides that, tell me about your journey with the American Auto Station. How is going? You're nominated for the Impact nominee, right?
Yes, thank you so much for asking. Yes, I am the American Heart Association's Woman of Impact here in Southwest Florida for 2026, which means it's my duty to bring awareness to women's cardiovascular health, research, innovation. This week, we are talking and putting a focus on your history, your family history, and what does that mean to you personally? So, women are not doing well with cardiovascular health in this country and around the world. So what can we do to make that better, to improve it? So that's what our mission is. It's to spread the word. It's awareness. And today in this week, we're asking, look at your history. What about, does your family have diabetes? Does your family have a history of heart disease, cardiovascular disease, heart attacks, cardiac arrest? And should you take a little minute and look at yourself and see what we could possibly do to make that better? So yes, thank you very much for asking. We are also raising funds for that. So, and it is a competition. So I am not afraid to say to our viewers, you can easily stop by my rescuern.com website or find me on LinkedIn to see if you'd like to join us. But other than that, I'm excited more to talk about our guest this evening. And, I don't think people understand how many varieties of engineers there are as much as how many varieties of physicists there are. Do you think?
Yeah, that you actually the guest who is going to come up is more closer to your kind of field than my field. Is safety, patient safety. Nurses deal with every day. You are one of the doctor of nursing practice. You deal with the nurses morning to evening. This is safety is a patient safety is people is a very not opaque to the public in general, how much involved in the patient safety of the measurement framework works, safety framework works, we have no idea, just we all take it, takes that as a granted, So let me introduce our guest, Noel Eldridge. I think I said his name is right. He's a
Yes.
guy joining from Washington, D.C. He's joining from Washington, D.C. He is a very well, one of the senior most leaders in the senior most leaders in the patient safety industry. He worked in the VHA and the defense and every federal organization.
Civilian population. I mean, that's one spectrum to across the whole spectrum. So patient safety guru in the house this evening.
Yes, so explain yourself a little bit. Give a background of yourself, Noel.
Okay.
Because we're not,
Thank you,
give a
Ramana.
background,
Thank
it
you.
would be good.
And thank you, Susan, for inviting me. So why don't I just give a little bit of background on myself in terms of my education and my jobs, and then we can talk about the specific patient safety things that I've worked on, and we can maybe go into some detail as the ones that are interesting to you. So as you said, I'm Noel Eldridge. I actually retired from the federal government almost a year and a half ago now. And but I had my career in Washington, something like 37 years, working for different science organizations and engineering organizations and biomedical organizations in Washington. My first job was at NASA headquarters, which is a very strange place to start a career, but it was excellent for me. It was the life sciences division at NASA. So they hired biomedical engineers, which is what I had studied in school as a graduate student at Clemson University. I had a degree in bioengineering. It was also known as biomedical engineering interchangeably. And my first degree was in mechanical engineering. And just since you were talking about engineering degrees, there are four main engineering topics that pretty much every engineering school has: mechanical, electrical, chemical, and civil engineering. Those are the core four engineering majors. And I did one of those as an undergraduate, which was mechanical. And then a lot of larger schools will have different majors like bioengineering, nuclear engineering, aerospace engineering, goes into many different varieties.
Yeah,
But
that was
anyway,
my point. So thank you for saying that there's just so many.
There's many, but there's four core ones. And I did biomedical engineering, and it worked out to get a job at NASA headquarters in the life sciences division because they needed people that understood biology and understood machines because I was working on the space shuttle experiments that were going to go up in space on the space shuttle on a mission called Space Lab Life Sciences 1, which flew in 1991. And so a little bit after that, I went to work at the National Research Council, which works with experts to give guidance to the federal government on scientific and engineering topics. I worked at the Aeronautics and Space Engineering Board there, and I worked on a project for life support systems in space, and we wrote a whole report on that for NASA. And then after a few years after that, I went to work at the American Institute of Biological Sciences, where we did all kinds of reviews of proposals for federal agencies, including primarily the U.S. Army's medical research programs. We would bring in experts to review proposals and grants and things like that to see if they were appropriate for funding. Whenever there's a funding announcement, as you might imagine, whether it's the NIH or the Army or the Agency for Healthcare Research and Quality or wherever, there's always many more applications than can be funded. So you have to have some kind of process for picking the best ones. So I was involved in that process for 4 years. And then I got hired to work at the Department of Veterans Affairs National Center for Patient Safety. And I was hired to work for Dr. James Bajan, who was actually the chairman of the committee I worked with at the National Research Council several years earlier on life support systems for space. And so I worked there for about 9 years. And the people that know me from that work know me for a variety of things, but the things that was most well known during that period were working on patient safety programs and initiatives and policies around two main topics. I got into a lot of other topics, but two main topics were infection control, and the other one was safe surgery. And with infection control, it was a very interesting time because in 2002, the CDC had put out a new guideline about hand hygiene, which sounds like a really boring topic, but it's basically everything about when you should wear gloves, when you should use soap and water, when you should use alcohol hand rub, and in what contexts to prevent the spread of microorganisms around hospitals, whether it's onto patients' bodies or whether it's onto elevator buttons, doorknobs, or whatever, spreading these potentially pathogenic microorganisms around hospitals. And so hand hygiene was a very important topic. And the new CDC guideline was the first major document that affirmed or identified that alcohol hand rub was probably better than soap and water for disinfecting hands. And that was around 2002.
Mm.
And when I read that, I realized this is going to change everything, because it was just impossible to wash your hands with soap and water every time you would need to do it according to the guidance, because your hands would get, damaged from all that washing in a single day. A typical nurse or a typical doctor that's seeing patients on a regular basis. But it wasn't impossible to use the alcohol hand rub that frequently. So that became a big topic, and we actually published. I found out many years later, the first paper using the Six Sigma method for quality improvement in healthcare on hand hygiene improvement in the VA. The paper we wrote on that and published in the Journal of General Internal Medicine was the first Six Sigma project that was published on healthcare in history. It's a little small claim to fame, and
yeah.
and
So
then,
you just took something that you said seems so ordinary and small, washing your hands, to the first published paper on it, and it is a really big deal in the hospital, washing your hands.
yeah, of
Big,
course. So of course, there's many papers on hand hygiene, hand washing, things like that. The CDC guideline had 450 references in it, if you could believe that. It was and they had like 40 odd recommendations in there to try to figure out those recommendations and boil them down into things that people could understand was a big challenge. The paper that we wrote was the first one that ever used the Six Sigma quality improvement method to improve in any healthcare topic, whether it's hand hygiene or anything else. That was the first Six Sigma paper that
No,
we.
can I ask you? I hate to interrupt, but I
No,
you
good.
said twice you said something about life support systems in space. I have to ask, what do you mean life support systems? Like ventilators, like people, like if there's a problem
Good
with
question.
the
Well,
astronaut?
if you're in space, right? Think about it. There's no air, right? In space, but you live in a little bubble, a little metal bubble full of air that has to have clean air, and it has to have the right amount of carbon dioxide and the right amount
So
of
normal
oxygen.
life support systems for a well astronaut, not an unwell astronaut that needs life support services or
Yeah,
systems.
no, the life
Okay,
support of
feel
the
better.
whole the space station, basically the space station, the space shuttle, any future missions to Mars. You have to keep you have to you have to have the right amount of oxygen, obviously, right? That's the most
Yeah.
important thing. But then the other things are tricky too, because all the plastics can off gas, and that doesn't usually matter. You open the window or something. If you get a new uh, uh, memory foam mattress or something in your house, and it's that has a strong smell from all the plastics coming out, or you
You're
just open the
stuck with
window
it.
or something. But if you're in space, these things are super
Interesting.
important. All these
All right.
weird things. So there has to be all kinds of methodologies to keep the air clean, and then also that the water has to be recycled,
Yeah.
because
Yeah.
you can't bring up enough water. So there has to be a lot of water recycling. And then we had
Interesting.
people that were talking about using plants in this process in the long run, because plants, you give them light and they produce oxygen and they use up CO2. So there's a lot of things to consider. Anyway, that's not what I'm here to talk about.
Oh,
But
I'm sorry. I'm sorry.
no,
Curveball.
I
Back
love
on
this.
track. Back on track.
I love that topic. But I got out of the space program when I was around 30 or something. And I give myself credit, because at that point I kind of felt like there probably wasn't going to be a mission to Mars in my career, and now I'm 61 and there's still been no mission to Mars 31 years later. So I just kind of felt like, hey, this space program is really interesting, but there's nothing major coming up in the next few decades. I'm born at the wrong time, I wasn't born for the Apollo program, and I wasn't born for maybe 100 years from now when there's other interesting things going in space. Anyway, so I went to work at the Department of Veterans Affairs National Center for Patient Safety, working for Dr. James Bajan, who was a former NASA astronaut, and he hired me to work there. And I worked there for 9 years, and I said I worked on hand hygiene, surgical safety. The main thing we focused on in the beginning was preventing wrong site surgeries. And that was one that there's a phrase in health law in the class I took, which is called res ipsa loquitur. I hope I have that right. I'm not a Latin speaker and I'm not an attorney, but that means the thing speaks for itself, which means that when that thing happens, there's no argument about that it shouldn't have happened. Everybody agrees that should not have happened. And wrong site surgery is one of those things.
Yeah.
And
there was a movie actress came from India. Her mother was a very popular lady, very famous actress. She was operated in New York City. She was operated on the wrong side of the brain.
yeah.
They thought in the left side. I was surprised how could it be possible that is. Now you're telling me that is a very common problem.
No, I didn't say it's very common. It's not very common, but it's one of those things that
Not uncommon, at least.
yeah, no, it's one of those things that was maybe 1 in 10,000, 1 in 20,000, and it should be like 1 in a million. That's the way I look at it.
Okay.
It's the kind of thing that should almost never happen. It should be like a plane crash or something. It shouldn't be it should be something where when it happens, a whole series of things went wrong. People tried to do the right thing, and somehow it managed to happen anyway. But that wasn't the case. It was happening much too frequently. Like in the VA, we were doing like 300,000 operations a year, and it was happening like once a month, like 1 in 30,000 operations or something. So that was just too common. That wasn't tolerably common. You know what I mean? If it was once every 3, yeah. Go ahead.
So then what'd you do about it? Because I think, when you're in
Yeah.
a setting like the VA, you have an opportunity. I think standardization is probably easier in the VA than maybe anywhere else. I don't know. Maybe you'll be able to go from your VA experience to your military experience. But I think both in those places, I'm just guessing, I'm asking, would standardization of whatever protocol you came up with to help fix this be implemented easier in VA and military than it certainly is in civilian world? So I'm curious as to what you did.
You've probably well, maybe I don't know if you've heard that the Joint Commission had something they called the Universal Protocol that they put out there for preventing wrong site surgery. Well, our work was a precursor to that.
Okay.
And so the things that we focused on, we didn't invent these things. We just put them together in a package that was tolerably, not intolerably complicated or arduous, time consuming, because, you don't want to add a lot of complexity or time to preventing to getting the operation started, right? You just want to be able to add a few little things that really don't add any complexity or time to the procedure. You don't want to get in the way of the surgeon doing the surgery.
No,
So
yeah.
the things that we did were just basically requiring the site to be marked by a surgeon before the procedure starts, like when the person's in the waiting area. When the doctor visits with the patient before they do the operation, they can mark the site. And they can mark the site with the patient being present and not when the patient's asleep, so the patient can participate in that. And then it's funny, I'm looking in looking there in my right here, I have a poster that we put up, a copy of that poster that we did 20 years ago. So the first step, actually, I skipped over, is the consent form. To make sure that the consent form's in plain English, so that the person knows, they can see on there it says left knee. It says left kidney or whatever. Like one of the examples I used to give to non-medical groups would be, if I told you we were going to perform a bilateral nephrectomy on you, how would you feel about that?
Not so good.
Well, you're a nurse, you know that.
No, thank you.
Romana, do you know what a bilateral nephrectomy is?
And mastectomy?
No,
it's taking out both of your kidneys.
Yeah, no.
So that's why. So you don't want to put that. You don't want to put that on the consent form. You want to say removal of left kidney or something, if there's kidney cancer or something, you know what I mean? So these kinds of things. So that's the consent form. The next thing is the marking the site. And then the other thing is making sure you have the right patient. So that is asking the patient their name. You see this all the time now, but 25 years ago, this was not common. When you go to healthcare, they're always asking you your name. But in the past, they used to tell you your name and you used to say yes. So they might say, okay, are you Susan Davis? And you say yes. But maybe they might say Susan Davids or something like that, you know? And maybe you might be hard of hearing. And then it can never get people. We would find out cases where people had similar names, and that's the reason why they got the wrong operation.
Yeah.
So those kinds of things. And so I'm not going to spend all night on that, but this is one of the things that we focused in on, was getting the wrong site surgery problem addressed as well as it could possibly addressed throughout our system. And then in the aftermath, from my perspective, the nation jumped on top of that with the Joint Commission doing the universal protocol after we'd already done it in the VA. You know, we were about 90% the same as what Joint Commission eventually did, and we'd shown it was able to be implemented in the VA system, and a lot of people get trained in the VA system, obviously. So I think that was a pretty good success story for us. And anyway, so I worked there for 9 years on many different things. Another thing was just establishing what the patient safety programs at the local hospital should be like. What are the responsibilities at all the different 150, 160 VA hospitals? What kinds of things have to occur at every hospital to be compliant with the national program? And so that was.
Can I ask you to that's an interesting pause part, I think. So what kind of things, you said across all the hospitals, do we want them all to be watching for, looking for? Can you narrow that down for us, whether you're in the VA or you're in the public sector? What is the core of patient safety? What are the things we're looking for? Or you know, from your lens, I would say, from patient safety lens, what are the top 4 things that a hospital's watching? You mentioned hand washing, you mentioned wrong site surgery, but now like some meat and potatoes.
Yeah, so you know, the hand hygiene situation is, you know, thousands of times a day potentially, you know, and then the surgery thing is a much more isolated thing. The kind of thing that we were trying to establish throughout the VA system, and has also been established nationwide to some extent with Joint Commission requirements, is responding to accidents, adverse events that occur, and close calls or near misses that occur in a serious way. So the example, Romana, you gave of somebody who had a wrong site surgery on their skull, on their head, on their brain, whatever it was, somewhere there. Like I had somebody come up to me once when I was talking at a briefing conference, and they said, well, you know, we shaved the wrong side of somebody's head, but we didn't actually do the wrong operation on them. We realized it after we shaved the wrong side of the head. And that kind of thing should be a wake-up call. If you get that close to almost, you shouldn't wait until you actually do the wrong side of somebody's brain. So we tried to focus in on taking these near misses and these close calls very seriously, and then figuring out what went wrong to that point so you can fix it before it actually turns into a disastrous event. You know,
what is an adverse event? Can you, or what are the top 3 or 4 adverse events we might be thinking about when we're talking about patient safety?
Well, adverse event is just the kind of the jargon that we use, right? Adverse, what does that mean? Bad, right? Event is a thing that happens, right? So what's an adverse event? It's a bad thing that happened. That's plain English of what an adverse event is. And so in the work that I ended up doing at the Agency for Healthcare Research and Quality, we broke them into 4 main groupings. Like, for example, adverse drug events. The classic adverse drug events are things like the wrong route, the wrong patient, the wrong dose, all that kind of thing. But then we saw a lot of cases in our data where the person got the intended dose of the intended drug with the intended route and everything else, and still had a bad reaction from it. Like they got a hypoglycemic agent with the intended dose, but it drove down their blood sugar too much, below 50 milligrams per deciliter. I think this is a measure. So these things, we would look into them, even, the classic wrong dose, wrong route, those kind of things, overdoses. Even when the right dose is given, there can be an adverse event. Somebody can go into a coma, something like that.
So medication errors are one of the biggest ones.
Yeah, medication. So sometimes it's an error, like somebody gets the wrong drug or the wrong dose. But sometimes a person can get the correct dose, and it can still have an adverse event from it.
Adverse for them, because sometimes with
Yeah.
patients, the moon, the stars, and the barometric pressure align just so. And did they check? Was it a diabetic patient? Did they check the blood sugar before? There's lots of humans.
Well, there could be a misunderstanding of the patient's weight or something like that. Any kind of things that could happen. One of the things that I remember when I first started working in this field was adverse drug events with fentanyl patches. And a fentanyl patch. Have you seen this one,
Oh,
Susan?
sure.
Yeah.
Big
So
time.
a fentanyl patch is basically a sticker that you put on somebody's shoulder or something, or their back, and it just very gently and slowly lets fentanyl get into their bloodstream. So, and that's a good thing because it's producing people that have chronic pain. At least at this time, 25 years ago, that was recommended kind of treatment. So somebody might show up at a hospital with a fentanyl patch already on, and they're complaining of really terrible pain. Assuming legitimately, forget about people that are, drug abusers or something like that. Somebody legitimately is having a really severe amount of pain, even though they have the fentanyl patch on. And if the staff at the hospital doesn't realize they have a fentanyl patch on and doesn't either inspect their body, ask them questions, check the patient record, back then it was harder than it is now. With electronic records, it's easier now. But they might give somebody an opioid by mouth or an injection to like Demerol or something like that. And here I'm going a little bit out on a limb because I'm not a pharmacist. I'm not an expert on all these different drugs. But basically, you could give somebody an opioid on top of their fentanyl patch, and next thing you know, they're in danger of stopping to breathe and dying because they just got an overdose of opioids, because fentanyl plus whatever else they got is going to give them respiratory depression and kill them.
So what I'm hearing, Noel, is that there's really an almost infinite amount of areas where we can make mistakes. We are human.
I've been looking at this for a long time, and I don't think it's one of those things with an 80-20 rule where 80% of the problems come from 20% of the issues or something like that. There's a lot of different things, and the main thing is we focused on at the VA was looking at your local problems and your local close calls and doing deep dive root cause analysis on those to really understand what was going wrong at your hospital. Because even though the hospitals are similar, they're all different, And
it's
so
culture. The culture is different. The safety culture is different. And you're only, and in my world, I work a lot with failure to rescue. I'm a resuscitation,
Okay,
I work
great.
So failure to rescue is in my world. And so that's a whole can of worms in probably in your knowledge and language. So how far upstream can we get? And then I'm just going to go ahead upstream of the issue. So how many hours before an episode of whatever, I will use my specialty, cardiac arrest, does a patient show signs and symptoms? And do we catch it? And so no matter what, I guess my question to you will be based on what I'm speaking about failure to rescue is, I often teach that the early warning systems we have in place, many of your patient safety things that you probably will speak about for the rest of the show, they're really only as good as the humans that input into them and how they input into them. So you're into data collection, you're into watching these numbers, but we don't necessarily all chart the same. We don't write the same way. Some click box, some type more, some do it timely, some do it post fact. There's so many variables in helping. I'll use my one example, failure to rescue.
Yeah, no, and that's a super important topic that you're working on, failure. making sure that
Well, I have a
people.
question for you. When a patient dies during the surgery or post what Susan is saying, cardiac arrest or whatever the situation is there any safety protocols trigger back and you retrospectively you check the safety measures? What are the things can went wrong or something like that? Is there any way a checking mechanism is there?
Root
What
cause
could be the
analysis,
cause
right?
of that problem?
Well, I mean, that's a big question, and I can't claim to answer it perfectly, but the first thing to consider, was this death a totally unexpected death? Was it an expected death, or was it somewhere in between? You know, if it's a totally unexpected death, then it's something that needs to be considered in depth by many different people involved. Like, I know somebody that I've worked with in the past that had a family member, die suddenly uh, in the hospital, and they died from a drug that caused a GI bleed so severe that they ended up bleeding to death internally into their digestive system. And so
Isn't it?
that wasn't apparent as they were dying. They didn't catch it. They didn't know what was happening, and the patient died. But then afterwards, this was somebody that was recovering from a normal surgery. It wasn't expected that they were in danger of dying. They were young.
Which is
So,
nearly the definition of failure to rescue. It's when a patient dies in an unexpected way from something that we could have, should have caught and been able to manage prior to the death. It's kind of the definition of failure to rescue in the hospital setting.
Isn't it that important is that any death should trigger the safety protocols review for that particular patient? Is there
well,
any method is like that, or you don't care?
I,
Only deaths, expected deaths here, unexpected death is only measurement that you do. Do you do the
well,
safety measurements on all
no,
the deaths in respect of the?
this isn't exactly a rule of thumb, but I remember someone in my career said to me, someone that was more senior to me and more expert in healthcare than I was, said that nobody should be dying in the hospital that isn't in the ICU or doesn't have a DNR, do not resuscitate. That's where people should be dying in the hospital. If they're out in the ward in the bed and they have a do not resuscitate, and they have a cardiac arrest or something, and they have a do not resuscitate, then they're going to die, right? Is that right, Susan? If they have,
Correct.
and then somebody that's in the ICU, they have
Hopefully,
say they have
hopefully correct.
right, say they have severe burns or something like that, and you're trying to save their life, but they just can't be saved and they end up dying. These things are not. I mean, you could still consider them something to look at, but there's no conspicuous adverse event there. We're all going to die, and some of us are going to die in the hospital. And the best thing that can happen is in a sick sort of way is that you die from your disease when it can't be cured, rather than you dying from something else, like some kind of mishap in the hospital, like you get an overdose of a drug or something like that, or you slip
Well,
and
the
fall. And
medical examiner ends up weighing in on every death that happens inside the hospital walls.
yeah, there
So
has to be a cause of death just attributed to the death. I mean, and then that can vary widely from state to state, hospital to hospital, hospital system to hospital system,
sure.
all kinds of protocols around that.
Yeah, both you are experts in safety protocols. I know that, but the reason I mentioned that because I am developing some kind of a framework related to that kind of thing, the future safety network, and so I'm going to present that topic right now, and then come
Oh,
back and we'll come back and
Well,
ask you
I
what
think
is
this
your
is one
input
thing.
on that one.
This is one thing that you raised to me in some of the back and forth before the call. Is that I think this
Yeah,
is one area where AI will be able to contribute a lot in the future.
yeah,
yeah.
that's
Look
exactly that's what I'm going to
look at
do.
the patient record and say, is this normal or is this abnormal? Is this what happened? The AI may not be able to figure out what happened, but it may be able to figure out this wasn't supposed to happen. And then people
Yeah.
can get involved in figuring out what happened when, excuse me, when this is a really extraordinary, inappropriate death.
Hmm.
Yeah. So just the reason is one of the measurement in that aspect comes in this picture. But anyway, let me talk about, I was talking about I did a 4 series so far I've done. Susan knows about it. And I did a 4-part series on the AI's influence in the healthcare system. What are the things it limits? AI limits the healthcare, is that you can jump in anytime, Noel. If I mistakenly say something wrong or violated something, you can always, both of you can jump in. But the first one, I tried to explain the first series one, that first talk I did is in the black box. A lot of people think is a black box is a something. Susan talks about black box in the FDA side. That means unknown outcomes, some other things. But it's much more serious than that. That in the AI black box is much more serious. There is a several actually black boxes exist in the AI. One black box people talk about is technology kind of black box. Through the good tools and the time and the knowledge, we can solve that problem. Probably the black box one type. There's a black box 2 type, which is there is no way you can reach structurally inside. Like looking at your grandmother's photo in your brain, you cannot find it. So that is not possible. So that is so that structural limitation is there in the black box number 2. Black box number 2. Black box number 3 is until you finish the computation, you don't know the final result. So you will not know what that outcome is. So you cannot predict what the outcome is. So it's kind of serious. So if you combine all the black boxes, it's kind of scary a little bit in that sense, because the second and second black box and third black box combined together, fourth black box, which is inside you don't know what's going on, and then outcome you cannot predict. That is the combined. That is a dangerous one. We have to watch out. That's where the guardrails come in the picture. Even if guardrails helps or not, we don't know. That is a black box. It's a serious problem. People really misunderstanding or lack of understanding about the black boxes. The second one is I talked about the irreversibility of the biological systems, because it's a thermodynamic. Entropy always increases. Is a thermodynamics. The order to disorder is a natural progression. You cannot reverse it back. You cannot do operation undone. You cannot do a lot of things undone in biology. You can trigger the computer and go back and start the original program. You can't do that in the biology system. It's a life and death, right?
Yeah,
So
yeah.
it's irreversibility. It's not a possible. The third one is I did a entropy information.
I can't uneat that cheeseburger that I ate.
Yeah, correct. The third one is entropy and information. I did that. When you install AI, a lot of people think AI can solve one problem. For example, I give you one example of that is if you try to reduce the volume, and then AI can do wonders in that direction. But what happens is when you put AI and gives you summary of all the charts together, a patient's 90-year-old patient, it gives it the last 30 years of summary, it can give it to you. But you're not reducing the problem, because the entropy, the disorder, the information, cognitive load, you move to the doctor. Doctor has to worry about that information is correct or not. Is a cognitive load is increased. So it is a give and take. You got to be very careful. It is one problem is solved and shifted the problem to a different place. That's called entropy. Entropy shifting from one place to other place, even with AI. There's no escape to that. That's why you have to minimize how to do that. You cannot randomly put AI and say it will solve the problem. Basically, you're shifting the problem to someplace else. That is an entropy problem. I talked about part 3. Part 4 now, I'm going to talk about energy and power. It is a bigger topic now. Why our human brain works on 20 watts power. The rate of flowing of energy. It's a 20 watts brain works in 20 watts. Like a light bulb, we put a small 20 watts light bulb, basically our brain, electricity. You know, this simple rack, one GPU rack, graphic processing unit rack, NVIDIA rack, consumes 120,000 watts. One rack, okay? Think about that, 600,000% increase in the just not even a human cognition, it's just the thinking or memory or some small thing. That is a 600,000% increase in the human brain into the computer. So when you move from a human brain cognition to the human brain to the GPU, that's a biological to. When you move this biological to the biology to industrial, you're changing the entire system. Your biology to industrial is a very different ballgame. So one brain of 20 watts per con is if you want to simulate a brain, there's not even 100% very fragmented parts of the brain to simulate. You need a 1 million times more power. That is 167 GPU racks are needed. It's a whole entire system takes entire floor. Think about that. So the power requirements to simulate even a part of the human brain, even the lowest common denominator of human, you take it to do the simulation, you need a 1 million times more power than required. That is astonishingly, the biology to industrial transfer is one of the biggest energy expanse. So every prompt you do on the AI, if people think it's so simple, it's nothing, it costs almost 3 minutes you can put a LED bulb, 10 watts bulb, 3 minutes, it can light up one prompt. So 4 billion prompts a day we do. The energy that consumed by that is humongous. Electricity for hundreds of thousands of homes you can light up with the prompts itself. 10 million, if you do 10 million videos overall all over the world, altogether 10 million videos can cost electricity for Fort Myers, someplace where she's there, Susan is there. So it can take the entire electricity of the one city, about 10 million per year. So electricity consumption is just the explosive consumption of energy required for AI. People don't underestimate this process. So what is AI? This 1.2 trillion. Another problem is water.
Yeah.
It is the biggest challenge is water cooling. You need a 1.2 trillion water estimation. That is a liters of estimation required for the cool these GPU racks.
Well,
that is,
I mean, these are all engineering problems, right?
truly engineering problems, truly complex engineering problems.
I mean, for example, some of these things, for example, the electricity problem and the cooling problem, it's going to potentially lead to putting some of these places in. I would think in the future, people will be putting these places in Iceland and Newfoundland and places like this where they have tremendous amounts of cold water, and they have Iceland's got tremendous amount of geothermal energy. They already bring raw aluminum to Iceland to be smelted because they have a lot of free electricity there because of the geothermal power. So they bring aluminum. They don't have aluminum anywhere near ice. They bring it to Iceland to refine it into aluminum because it's very energy intensive. And they may end up doing the same thing. These are problems that they're new problems, but they're all solvable problems.
They're all
not easily solvable, but they're all solvable. All you have to do is turn New Mexico and Arizona into one big series of photovoltaic arrays, and you've got all the electricity you need. Build a bunch of batteries, and you got everything you need. So.
But the problem is Virginia, for example, has the highest number of data centers.
I know. I've been there. I've been driving around Virginia, and there's these data centers all over the place.
Yeah.
It's
so
crazy.
Their water is not. You can't get that much water in Virginia itself. No. I don't think they can get at that water. So that's a problem. Is a state.
Well, there's plenty of water in Virginia. The problem is probably electricity in Virginia.
So there's a water and electricity problems are huge problems, engineering problems. They need to solve that. And also, on the top of it, you're talking about data centers cooling, but the production of that water, transport of that water, and then the thermal electricity, the power plants, the cooling of the power plants, indirect water consumption is humongous. So
Yeah,
water
but
is one of
the
the
water's
biggest.
not being the water's not being destroyed, right? It's not like burning gas. It's just
Well,
being made.
it's
It's just
some of
being
the
made
water.
hot.
Yeah, some of the water turning into heat, right? So
Yeah.
that becomes a vapor. So that is still, you have to use energy. There's not a free
Oh no,
energy there.
I'm not arguing with you about that, but it's not going anywhere.
It's
It
not going
just needs
anywhere.
to be recycled, and it's a horrible problem to have.
But yeah,
But
that still costs energy. That's what my point
yeah,
is.
no, no kidding. No,
Yeah,
it's a
yeah.
horrible problem. Yeah.
So is the energy burned by AI converting into health healing clarity? Suppose at what point in the AI is a value to the healthcare itself? It's a clearly modifies healthcare. I'm talking about just purely healthcare. AI, is it transferring that into clear clarity where the trust and time and the healing all is producing or not? We can quantify that. It's not that difficult to quantify whether you can take the AI energy into whether AI, the amount of energy you're spending on the AI, is it producing that enough quality of care and then trust and the time. You can create a formula for that. That's what I did actually. I created some kind of a hospitals can evaluate AI using three measurable signals. They can evaluate AI. One is a time impact. Of course, that is how much time they're spending. They're seeing more patients, for example. And they're spending more time with the patient. That's one of the outcomes of that. If you install AI, can they increase more time with the patient, or can they
Right.
see more
Right.
patients? Or
Right.
clinical outcome impact. You can see that you understood the medicine better, then you got the better medication dosage. All those things are, a lot of them are changed or not. A third one is the energy cost, how much the energy cost of the AI. At certain point, AI is not going to produce more results than we required because it is reaching the optimizing point. So you just keep on, just a minute, yeah. Let me so AI is powerful, deeply deploy with a clarity of outcome. If you deploy with a clarity of outcome, it is a really powerful. But if we just randomly put it there, there is a point that it will not produce any more healing, more than that can produce. It is a noise. After a while, it becomes AI becomes a noise. Too many alerts, too many data, too much data. It has no meaning to the humans. So you have to be very carefully balanced out. You can measure these things carefully. There is a new kind of a computers are coming in. They may solve this problem. It's called neuromorphing computing. So they simulate the brain more neurons into the computers. It requires a lot less amount of power than the present day computers now, the GPU racks. So eventually, this AI has to be clearly balanced way you have to install it. It has to make a sense. At the end of the day, it has to make sense because by putting AI everywhere doesn't mean you are producing more healing and the healing capacity. You're producing the more outcomes. So you have to find out that where that optimization is. So I created a MedBix predictor. Is one of my favorite sit
Yeah.
down.
Well,
Yes, yeah,
well,
that's what I did.
let me give you an analogy. It just came into my head. I mean, AI is brand new, right? I mean, it's just a few years old, and nobody knows exactly how it's going to pan out and how it's going to be used in healthcare and many other fields. But even things like this, I don't know if you've used some of these AI tools that'll listen to a whole teleconference and then write a summary. It's astounding what it can do right
It
now.
is astounding.
But I don't know how useful that is in healthcare. I mean, it's probably good in some things, But the thing
But
that came to mind,
if I do 5,000 podcasts, you got a 5,000 reams of the information is not
no,
useful. I mean,
no, yeah, I
it's
understand that. But
really,
what I was going to
there
say
must
is,
be a,
like, when people tens of thousands of years ago, no, not tens of thousands, but thousands of years ago, developed iron, right? There's a new material. It never existed except for, like, people found it in a meteorite or something. And that was very rare. And then people figured out how to develop iron. Did they know where that was going to go? Did they know they were going to build shovels from it, and hammers and screwdrivers and cars and trucks? No, they didn't know what was going to come. But they knew they had a hard metal, and it was unlike anything they'd ever seen before because it didn't get dull easily, and it was very, you could produce it at a large scale. And I think I think AI is like that right now. We've got a new thing. It's like a new hard metal that can be used for all kinds of things, and we're just trying to figure out what they are right now.
what they are, yeah.
Yeah,
Still,
but
you
I
got
think
to
there's, sorry, Romana, but and I think it was in black box number 3 when you discussed entropy. And one of the poignant things for me from that presentation that just I was reminded in this one just now was basically trading entropy for entropy. I mean, we've got a lot of noise in healthcare right now, and we think, oh, we've got this magic iron, and we're going to use and meld and mold and melt this thing into this great thing that's going to help us, but it's really a new set of noise. I mean, there's a million examples. Now we have physicians and nurse charting assistants, and it's charting, and the AI is picking up on it. Who's looking at that? We're
Yeah.
getting very lazy with this amazing tool, and it
Yeah,
quickly
so
does summarization. It quickly goes through they're done. Next patient. Who's reviewing that? We know they hallucinate. They know they take creative freedom. It just does. So I think entropy. I think I'm learning a lot more about entropy since hanging out with Romana, but I believe we're trading entropy for entropy.
Yeah, it is a good question. We need to be very careful, particularly in healthcare. People die, there's it's just adding, because salespeople talk a lot about, I put it in tomorrow, it will solve all your problems. But it's
Well,
not so.
let
You
me
got to
let me
be
tell
very
you.
careful how you do it. He's a safety expert. He can tell you.
Let me give you. Let me go into a little bit. One of the topics but we talked about a little bit before we actually came on the call was measuring patient safety.
Yeah.
And it's a very challenging thing to find these adverse events that were maybe not that conspicuous, like the ones I mentioned before, like anticoagulant events, like when somebody has a GI bleed or something, but maybe it doesn't kill them or it doesn't cause a severe, obvious symptom, but it still caused some harm to that patient. Maybe they reduce their hematocrit or other things that are important to having a good response to their surgery or whatever. And hypoglycemic agents, when people get too much insulin and it drives down their blood sugar, it increases the chance they're going to die in the next couple of years. Not just the fact that they managed to survive this coma from low blood sugar. They may still have a permanent deficit from that. So I think what AI and what computers are good for in general with people and combined with people, in my opinion, is if you have a big haystack, the needle in a haystack problem. You have a big stack of hay, little twigs, and there's a needle in there. You're trying to find a needle in a haystack. Well, that's the kind of thing a human being is very bad at, right? Because a human being cannot go through a whole haystack trying to find a needle with any kind of efficiency, assuming you don't have a special tool like a magnet or something to find a needle in a haystack. But the computer could probably go through that haystack and find out 20 things that look like a needle. And then the person could very quickly say, well, 19 things of those are pieces of hay that look like a needle. And then one of them is actually the needle.
That's a great analogy.
So I think that's the kind of thing that human beings and computers are good at doing together.
Yeah.
So you want the computer to say, you say you have a difficult diagnosis and I'm not a doctor again, but there's a difficult diagnosis to be done and they can't figure out what's wrong with this patient. They put all the lab data and all the notes and everything into the computer, and the computer gives you 5 different things or 10 different things to consider. Well, then the doctors might realize, well, there's 3 things on that list we hadn't thought of. And we already thought of those other 7 and ruled them out. So let's look at these other 3 and it might turn out to be one of those three things. So I think that's the kind of thing that computers will and AI will give us in healthcare.
Great analogy you gave.
Yeah.
That's a good analogy. Noel, yeah, Susan, you want to add? You're also a nurse. You know the safety protocols. You know what are the things you're missing? You think what are the things in the future? What do you think, Noel? What is one of the things that you or Susan you can answer? One of the safety protocol we should have done it. We should not have missed it. What would be that?
All of them. I mean, that's a big nut to crunch, Ramana. I mean, I think ultimately, Noel, and I'll let you close it out, and I'll just give. I just know from my perspective, from nursing perspective, and again, we touched briefly on my specialty, failure to rescue, and I work with resuscitation, so response, and so deterioration, the signs and symptoms of deterioration, and that's ultimately what we're talking about in any case. It's, are we catching the signs and symptoms? And how
In your case, is it training, right? And Susan, training is the key, right? Yeah.
Well, that's the kind of thing that AI might help with in the future, right?
Yeah.
Looking at those numbers.
It's very, very, very likely because again, but it's so multifaceted. It's so multi-layered. Why we're missing the signs and symptoms? It's not one. It's a stack of human issues. So yes, Noel, I do think and hope that and there's plenty on the horizon right now. Early warning systems that might help with the signs and symptoms of deterioration. So multifaceted, Ramana. Oh, did we lose Noel?
No, I'm here.
Okay. And so which ones should we have missed? You know, none of them ideally, but we're human. And I think that's my wrap up conversation on this is when it comes to patient safety, Noel's done a lot of work in the data collection, reviewing gazillions of charts, and the variability, I think, in the charting itself shows the humanness. So I love the prospect of AI coming in and helping us with the massiveness of this data collection, shining the light, if you will, on these certain couple, 3, 4, 5 areas that we hit the most. And Noel, you brought up things that aren't so obvious, but ultimately for me, it comes down to missing the signs and symptoms of deterioration and what can we do sooner to help and support our teams for catching it.
Thank you so much. You know, Noel, we want to say a final word, but I can tell you, thank you so much. Thank you for your service for the country. Thank you for your long-standing service. It's a purely great. You know, you're doing extraordinary work even after retirement. You know, you're providing people like us and the podcast like us. What are the safety protocols we cannot ignore?
Yeah. So I'll just say, you know, I was just gonna say I'm retired, but I'm still doing a little bit of part-time work here and there. And I've just been spending the last few weeks and trying to analyze the CDC's data on healthcare associated infections and the data that's available on the CMS Hospital Compare website that the federal government puts out that people can look at to understand what the data looks like for different hospitals that they may want to go to. And so that's something that maybe a year from now I could come back on and tell you all about that and how that turned out.
Okay. Thank you so much, Noel. Thank you for coming on the show. You know, you easily approved. Let me tell you, you are the first guest for this month, but we have an exciting guest coming in. Next week, we have, you know, there is India cancer immunotherapies, young entrepreneurs in India doing this immunotherapies there, and they started it actually. They're the new brand of a generation of people. And then after that, I have a very good news. The new Nobel laureate who invented COVID vaccine indirectly, mRNA messenger vaccine. She is Kathleen Cario is coming up. That's very exciting. So there is right now, so many things going on in Dubai. There's a doctor coming from Dubai. We know what's going on. And yesterday he was writing for me, you know, didn't answer phone for a while. I was worried about it. But he's coming on the show. He's from Dubai, joining in Dubai. And then Deepu Patel, one of the AI experts, is coming to join with us. After that, we have some investor conference, and Susan is going to join all of us. You know, so thank you, Noel. Thank you for joining with us. Good night.
Thank you. Thank you for inviting me. I
looking
really enjoyed it. Thank you, Ramana. Thank you, Susan.
Thank you
Thank
so
you,
much
sir.
for keeping our patients safe, Noel. It's a big, big job. You've done a long career doing so. Thank you so much for your work.
Thanks a lot.
Good night, all of you. Good night.
Good night.
We are retelling their stories through our patented designs that can be worn on scrubs, t-shirts, printed on conference bags, and endless other promotional materials. Daily Wear for Medicine is the first ever of its kind to create curiosity in medicine through visual art. We at MedBricks are celebrating unsung heroes of the past who made enormous contributions to the field of medicine through our unique campaign called Daily Wear for Medicine. You can wear it, carry it, and give it